Welcome to the RIC Mastery Course. Episode 1, RIC Fundamentals. Over the next 13 minutes, you will understand what a RAN intelligent controller really is. Not the slogan, not the marketing line, but the engineering object. What looks like where it sits in an open RAN network, why the industry needed to invent it, and the precise control loops that give it its name. By the end of this episode, the rest of the course will make sense as one continuous architecture instead of 14 unrelated topics. Let us start with the question that sounds simple but is rarely answered cleanly. What is RIC? A RAN intelligent controller is a software platform that sits outside the radio access network and steers the radio access network in real time. It hosts applications. Those applications observe the live state of the RAN, every cell, every user, every measurement report, and they send back policies and control commands that change how the RAN behaves. The RIC does not transmit the radio waveform. It does not schedule the symbols. It tells the things that do those jobs what to do. There are two RICs, not one. The non-real-time RIC lives inside the service management and orchestration framework. It works on control loops longer than 1 second, sometimes minutes, sometimes hours, sometimes a full day. The near real-time RIC lives close to the base station. It works on control loops between 10 milliseconds and 1 second. The two RICs talk to each other through an interface called A1, and the near real-time RIC talks to the base station functions through an interface called E2. Remember those two letters, A1 and E2. They will appear in every episode of this course. Why was the RIC needed at all? Why could the industry not just keep the intelligence inside the base station the way it always had? The answer is closure. The traditional radio access network was a closed system. The vendor wrote the scheduler. The vendor wrote the handover algorithm. The vendor wrote the power control. The vendor wrote the load balancing. If you, the operator, wanted to optimize for a stadium event on Saturday night, you opened a support ticket. If your competitor offered a smarter algorithm, you could not run it on your existing kit. The intelligence was buried inside vendor firmware that you could neither read nor change. The RIC breaks that closure. By moving control logic out of the base station and into a platform with open interfaces, the RIC turns the radio access network into something you can program. Algorithms become applications. Applications become an ecosystem. Operators can mix and match vendors for the radio hardware and then run their own intelligence on top. What does the RIC fit in Open RAN? Picture a vertical stack. At the very top sits the Service Management and Orchestration Framework, the SMO. The SMO hosts the non-real-time RIC. Below the SMO, you find the near real-time RIC. Below the near real-time RIC, you find the disaggregated base station, the O centralized unit control plane, the O centralized unit user plane, the O distributed unit, and finally the O radio unit. Between the SMO and the near real-time RIC runs the A1 interface, carrying policies and AI model artifacts. Between the near real-time RIC and the disaggregated base station runs the E2 interface, carrying subscriptions, indications, and control commands. And the SMO reaches every managed function below it through the O1 interface for fault, configuration, and performance, and through the O2 interface for cloud infrastructure. That single stack is the picture you should keep in your head for the entire course. Everything we discuss in the next 14 episodes plugs into one of those boxes or one of those arrows. Now let us address a question that telecom engineers always ask at this point. We already had self-organizing networks. We had SUN. So is the RIC just SUN with a new name? No. The differences are real. SUN, as standardized in 3GPP starting in Release 8, was a feature set baked into the radio access network itself. The optimization functions, mobility load balancing, automatic neighbor relations, coverage and capacity optimization, were implemented by each vendor inside their base station software. Sun was closed, vendor-specific, and slow to change. Adding a new Sun function meant a new software release from your vendor. The control loops were also limited. Most Sun functions worked at the cell level over minutes or hours. The RIC is different in 3 concrete ways. First, the RIC is platform-based, not feature-based. You install applications onto the platform. Second, the RIC is open. The platform exposes standardized interfaces, so any developer can write an application that runs on any compliant RIC. Third, the RIC introduces the near real-time control loop between 10 milliseconds and 1 second. That timing window was not reachable from a Sun function running inside the management plane. It opens up a whole new class of optimizations that simply could not exist before. Let's look at those control loops more carefully, because they are the heart of the RIC concept. There are 3 control loops in the RIC architecture, and you should know each by its timing budget and its purpose. The first loop is the real-time loop, faster than 10 milliseconds. This loop lives entirely inside the base station. It is where the max scheduler operates, where hierarchy feedback is processed, where physical layer measurements are turned into transmission decisions. The RIC does not touch this loop. The latency budget is too tight for any external software to participate. The second loop is the near real-time loop, from 10 milliseconds to 1 second. This loop runs in the near real-time RIC. Applications called xApps subscribe to streams of measurements from the base station, run their logic, and send back control commands. This is fast enough to influence handover decisions, traffic steering between cells, beam management adjustments, and interference coordination. The latency is bounded by the speed of light between the near real-time RIC and the base station, plus the application processing time. A well-designed deployment keeps the near real-time RIC within a few milliseconds of network distance from the base station. The third loop is the non-real-time loop, longer than 1 second. This loop runs in the non-real-time RIC inside the SMO. Applications called rApps consume long-term analytics, train machine learning models, generate policies, and push those policies down to the near real-time RIC over the A1 interface. The non-real-time loop is where deep learning happens. You cannot train a neural network in 10 milliseconds. You can in 10 minutes. That is what the non-real-time RIC is for. 3 loops, 3 timing budgets, 3 classes of intelligence. Real-time inside the base station, near real-time in the xApp, non-real-time in the RAP. The whole RIC ecosystem maps to those 3 layers, and as soon as you see them clearly, every other RIC concept will fall into place. Now we can talk about the most powerful piece, AI-driven RAN automation. The RIC is the place where artificial intelligence finally arrives in the radio access network, and it arrives in a way that is operationally honest. Training of large machine learning models happens in the non-real-time RIC on hours or days of historical data. Once a model is trained, it is registered, validated, and deployed. A small inference engine, the part that takes a feature vector and produces a prediction, is shipped to the near real-time RIC, where it runs inside an xApp. The xApp receives live measurements, runs the prediction, and decides what control action to send back. Predictions in milliseconds. Training in hours. The 2 layers cooperate. This is the whole point of separating non-real-time from near real-time. Without that separation, you would have to choose between fast and smart. With it, you get both. Where does a RIC get deployed in practice? There are 3 common scenarios. The first is a centralized deployment. 1 non-real-time RIC and 1 or more near real-time RIC instances in a regional data center, serving hundreds or thousands of base stations across a metropolitan area. Cheap to operate, easy to update, but the round-trip latency to the base stations becomes the limit on how fast the near real-time loop can close. The second is an edge deployment. Many smaller near real-time RIC instances pushed out to edge sites, each serving a few base stations. The near real-time loop is faster because the network distance is shorter. This is the deployment that enables sub-100 millisecond control loops for things like beam management. The third is a hybrid deployment, which is what most real-world operators end up doing. One global non-real-time RIC inside the SMO. Several near real-time RIC instances distributed across regional and edge sites. The non-real-time RIC manages policy across the entire footprint. The near real-time RIC instances handle the millisecond scale work close to the radio. Let us close with an honest accounting of benefits and limits. The benefits are large. The RIC unlocks multi-vendor optimization. It enables an application ecosystem on top of the RAN. It makes machine learning a first-class component of network operation. It gives operators direct control over algorithms that were previously locked inside vendor firmware. It exposes the RAN as a programmable platform. The limits are real too. The RIC adds new interfaces, new failure modes, and new security surfaces. xApp conflict, two applications trying to optimize different things at the same time, is a real engineering problem that we will dedicate an entire later episode to. End-to-end latency from base station to near real-time RIC and back must be carefully budgeted. AI model lifecycle management is non-trivial, and the entire ecosystem is still maturing. Specifications evolve. Service models change. Compliance is uneven across vendors. That is RIC Fundamentals. In the next episode, we will open the ORAN architecture itself, walk through every node in the disaggregated base station, and see exactly how the RIC interfaces plug into the larger picture. See you in episode 2.